Good. So, like I said, since we missed out on it on Friday, well, the recording missed out on it, you guys didn't, but I felt it wouldn't do any harm to go over it again. I wanted to make sure that I was clear on this point about stereochemistry and chemical reactions, and just try to drive that home a little bit more clearly, and also make sure that it fits onto the recording for today. And then we'll start chapter 11. In my usual manner, I'm going to try not to go too fast. I think I sometimes fail at that, but one thing I like about this course is that we can be pretty leisurely in terms of pacing. I don't feel like there's anyone breathing down my neck over that. Except, strangely enough, a few of you are sometimes asking questions about like the next chapter, and I'm like, whoa. Which I love it. I love the enthusiasm. I love the curiosity. Don't get me wrong. I love it. Years ago, I knew a guy who would say, it's easier to calm a zealot than to raise a corpse. So I'd much rather be in the position of calming zealots. So I appreciate that. Good. So one of the points I was trying to make on Friday was that it is certainly possible for an achiral starting material to undergo one of the reactions that we've discussed and give you either an achiral product or a chiral product. Both are possible. And we went through a couple of examples. I'll put them down again as soon as I find them. For example, if you take 1-butene, which is not chiral, and you treat this with hydrogen gas over palladium or platinum or nickel catalyst, any one of those catalysts will work, you will wind up with butane, which is not chiral. But you can take that same oops, wait a minute, I'm going on to the next one already. So my point being is achiral starting material and achiral product, that can certainly happen. That's certainly a thing. But you can also start with an achiral starting material and wind up with a chiral product. For instance, if you treated this with HBr, and even considering only the Markovnikov product, the one that Markovnikov's rule would predict as being the major product, there's now 2 different possibilities for this one because we've generated a chiral carbon over here. And so since we've generated a chiral carbon, that means we're going to have both R and S enantiomers. And you can draw them as such. What, can't see? Should I make it bigger? Oh, okay, I'll make it bigger. It's not like I don't have room. I don't know why I was making it so small. But we will get these 2 products. And let me figure out which is R and which is S. This one goes from bromine to ethyl to methyl. Looks like a right turn. This one's going to be R, and this one will be S. So that's a possibility. It's not like it's magic or something like that. It's a natural consequence of the type of chemical reaction. When you add HBr across an alkene, you turn the double bond into a single bond, and then one of the carbons gets the bromine, one of them gets the hydrogen. If we'd used HCl, then it would be a chlorine and a hydrogen. If it were HI, then it would be an iodine and a hydrogen. I should mention, by the way, the other hydrogen that comes from the HBr is over here. You don't have to show it, it's understood, but you can draw it in if you want to. The other hydrogen that's on the same carbon as the bromine was there to begin with already. But when we put that bromine in, when we install that bromine atom, it's got 2 choices of where it's going to go. It can point up or it can point down. And so that's why you get a chiral product from an achiral starting material. It's not magic, nothing up my sleeve, but that was mostly what I wanted to make you aware of, that you can also start with an achiral starting material and get a chiral product. That's also a thing that happens. it's also possible to start with a chiral starting material and get a chiral product. So for instance, if we started with, and I'll just use the same examples as I did the other day. Let's say we started with this alkene, this enantiomerically pure alkene, meaning it's 100% R, which would be very expensive to get your hands on, by the way, but that's another story. And let's say we treated this guy with HBr. Then we would expect to get two products, and I'll try to draw them nice and big. And notice that the carbon with the chlorine on it doesn't change because that carbon is not involved in the chemical reaction. The way we know that is because the alkene is what reacts with HBr. The other carbon doesn't react. That's not an alkene carbon. So that just is along for the ride. Nothing happens to it. But just like before, the bromine can wind up pointing up or it can wind up pointing down. So you get, again, these two products. And this one will be R. Let me now quickly do that one for you. Looks like, again, that's a right turn, whichever that way is. And this one will be RS. So whereas before we got a racemic mixture, and we've already defined that term, racemic mixture, meaning a 50-50 mixture of R and S products, or of the two enantiomers. A racemic mixture is a 50-50 mixture of enantiomers. Which, by the way, begs the question, this is a little bit parenthetical, can you have a mixture of enantiomers that's not 50-50? Of course you can. It's just not a racemic mixture. To be a racemic mixture, it must be exactly 50-50 or 1-to-1. Meanwhile, over here, you've got the RR compound and the RS compound. This is an S over here. So RR and RS are not enantiomers. Remember how we defined enantiomers. We said that when you compare two enantiomers, all of the chiral centers, in this case, all two of them, are going to switch S to R and R to S. So that's not the case here, because the carbon that's R is the same in both of them. The only one that changes is the other one, R and S. So the enantiomer of RR would be SS, not RS. But the reason we don't get any SS is, again, because this carbon over here is not involved in the chemical reaction. That's just along for the ride. That doesn't do anything. That doesn't change over the course of the reaction. And we know that by the nature of the reaction. We know that alkenes react with HBr and undergo an addition reaction. This is not an alkene carbon, so it doesn't undergo the addition reaction. It just stays the way it is. And so as a result, we don't get two enantiomers, we get two diastereomers. And I would expect they'd be in a 50-50 ratio. I don't see any reason one of them would be preferred over the other. But instead of a 50-50 mixture of enantiomers, I would expect to get a 50-50 mixture of diastereomers, which also begs another parenthetical question. Is there a name for a 50-50 mixture of diastereomers? Not as far as I know. I've never heard of any term used to describe that. Racemic mixture is used for a 50-50 mixture of enantiomers. In other words, stereoisomers that are mirror images of each other. And I don't know of any similar one-word description for a 50-50 mixture of diastereomers. Recall that diastereomers are stereoisomers that are not mirror images of each other. And again, because it's RR and RS instead of SS, we know these are not mirror images. So they're diastereomers. They fall under that definition. So that was really all I wanted to be sure that I covered. Most of the rest of what we covered on Friday was not new material anyway, except the material on meso compounds, which, as I said, I'm not going to say you don't have to know it. You do know it, but I'm certainly not going to emphasize it exceedingly heavily on exam number 2 or on the final exam. And you get to practice that concept on the OWL assignment. So I think that will all come out in the wash, so to speak. Good. Make sense? Just wanted to make sure that kind of got in the record of the class. Then with that, we are able to, oh, I guess I forgot to say one thing. As for a chiral starting material becoming achiral, That's not a thing unless it specifically racemizes the chiral carbon, which is not a thing we ordinarily know how to do. So if it starts out chiral, unless something really weird is going on, it's going to stay chiral. So that fourth one, I'm pretty convinced is not a thing. But the other three are all possibilities. Good. So with that, we can finally start in on chapter 11. Chapter 11 is on amines. And the relevance of the material on amines is, I hope, going to become clear as we go on to the chapters on nucleic acids, since nucleic acids contain lots of nitrogen atoms, and amines are an organic nitrogen compound. In fact, they're organic derivatives of ammonia. So please do review your functional groups. That's where we first introduced the idea of amines and defined them. But that's one thing. You'll also find amines and amino acids, and we're certainly going to do a chapter on proteins and polypeptides too. But again, from an organic chemist perspective, we're going to steer mostly clear of the biological function. Not because I think there's anything wrong with that material. It's just I don't think it's appropriate for an organic chemistry course. But that being said, at the same time, I am aware that this class is an introduction to both organic chemistry and biochemistry. But I do take that very seriously. So I want you guys to come out of this class with a solid structural understanding of what these biological related compounds entail: your nucleic acids, lipids, proteins and polypeptides, carbohydrates. Those are the four big ones, I guess. My goal is that if you take any upper level classes that involve biochemistry at all, you will have a good background for that and be able to understand those compounds at the structural level, because in my experience, that structural understanding is exactly not what they will focus on in upper level biology and biochem classes. This way, when you get to those classes, you can be like, oh yeah, I know what proteins are. I know they have this and that kind of structure. I know what nucleic acids are. That's my goal from all this. And it might be that you've already taken those classes. In that case, it's my goal that you'll be able to come out of that saying, oh, so that's what they were talking about back then. Now I get what a protein is. Now I get what a carbohydrate is. So hopefully it will fill in some of that information that's not as much emphasized in upper level biology and biochem classes. Good. So that's at least part of the reason why I think amines are important compounds, and you need to know something about how they behave. They're the type of compound you're going to run into, both in, well, certain amines, I hope not, but the sort of things that you will find in relevance to food science, food both for humans and animals, anything involving fertilizer, you're going to run into amines for sure. And anything, as I said, that touches biochem or biology, where biology and chemistry intersect, you're going to find amines. And indeed, we've already run into some in this class. So first of all, I think that's pretty key. I need to say that amines are organic derivatives of ammonia. Derivatives of ammonia. And I think we're aware that ammonia is NH3. By the way, just another side note, I always try my best to put things into context. You're probably aware that when you go to the store and you go to the cleaning aisle and you pick up a bottle of ammonia, you're aware that's not pure ammonia. That's an aqueous solution of ammonia. Pure ammonia is actually a gas at room temperature. So I don't even know how concentrated that solution is. I'd expect it's 5 to 10% maybe. And you're also familiar with how ammonia smells, not very pleasant. Most amines smell like that or even worse. They generally have very disagreeable odors. I'm hard pressed to think of a counterexample. They all smell kind of like ammonia. Amines also come in a few different flavors. We can speak of primary, tertiary, and secondary amines, and then also of quaternary ammonium salts. So a primary amine is of this type, where we have one alkyl group attached to the nitrogen. We call this a primary amine. Sometimes they abbreviate that 1 degree, like 1 degree above 0. A secondary amine, on the other hand, whoops, not carbon, nitrogen, would be a compound of this type. So there's 2 alkyl groups. And I will give examples of all of these in just a moment. I just want to give the generalities first. But secondary amines will have 2 alkyl groups attached to that nitrogen atom. Those 2 alkyl groups can be the same or different. It can even be incorporated into a ring. A tertiary amine, there I go with carbon again. Guess I really am obsessed with carbon. Would be a compound of this type. In other words, 3 alkyl groups and no hydrogens directly attached. We call that a tertiary amine. And last but not least, can you attach a 4th group? Sure you can, but then the nitrogen has a formal charge of +1. We call this a quaternary ammonium salt, which I was just about to misspell. Quaternary ammonium salt, because we want a plus charge on the nitrogen. Or a quaternary ammonium ion or something like that, quaternary ammonium species. These are species that no longer have a lone pair on nitrogen. And if you work it out, you can go back to that formula we gave way back in chapter 1. A nitrogen atom with 4 bonds and no lone pairs, which is better if no lone pairs, otherwise it has more than 8 electrons around it, which can't happen. So a nitrogen with 4 bonds and no lone pairs is a formal charge of +1. Meanwhile, the other nitrogens with 3 bonds and 1 lone pair, all have a formal charge of 0. So all this is pretty well to be expected. But I do want you to be aware of the different types of amines. I would expect you to be able to look at the structure of an amine you've never seen before and say, that's primary, that's secondary, that's tertiary, or that's a quaternary ammonium salt, even if you've never seen it before. But because by understanding the distinctions between these different types of amines, it has to do with how many alkyls and how many hydrogens directly attached to the nitrogen. So in terms of some examples of amines, I think the smallest possible amine has to be methylamine, and they're usually pretty easy to name too. You just name them by the alkyl groups that are on there. This would be a primary amine because there's 1 alkyl group and 2 hydrogens. What about something like this guy? You could call it diisopropylamine. Looks weird with the 2 I's right next to each other, but it's correct. And all one word, diisopropylamine. So that would be a secondary amine because we have 2 alkyl groups and 1 hydrogen attached. Let's see, what else? This guy, I don't think I really care if you know what it's called. We might get into some of these names. Let me make that bigger. I'm not doing a very good job at drawing things bigger. There we go, that's a little better. That guy happens to be called pyrrolidine. I don't know if I really care if you know that, but it does have a name. Now, would that be primary, secondary, or tertiary? Secondary, that's right. The 2 alkyl groups happen to be connected into a ring, but it's still a secondary amine because there's the equivalent of 2 alkyl groups plus 1 hydrogen. So absolutely pyrrolidine would be a secondary amine. An example of a tertiary amine might be something like triethylamine. And that's pretty straightforward to name, triethylamine. Just like that. So that'd be an example of a tertiary amine. One special amine that I think you already know the name of is aniline. Aniline is aminobenzene, A-N-I-L-I-N-E, aniline. So that's a special name. And you learned that in chapter 4 on aromatic compounds. So it's timely because it's still in this exam's unit. So what would be an example of a quaternary ammonium salt? Oh, actually, let me do one more primary amine. You would call that guy butylamine, because that's a butyl group attached 1, 2, 3, 4 carbons. You could also imagine what tert-butylamine would look like. So that would still be a primary amine. What would be an example of a quaternary ammonium salt? Well, maybe something like how about the tetrabutyl ammonium ion? Looks like a spaceship or something, but it's a nitrogen with 4 butyl groups. And of course, this wouldn't come, you can't have a cation without an anion, right? You can't have a jar full of ions. There has to be something acting as the counter ion. Could be chloride, could be bromide, could be bisulfate. Something's going to be there to act as the negative charge. But the organic species has a positive charge. And that would be an example of a quaternary ammonium salt. I suppose the 4 groups in the quaternary ammonium salt could be different. I can't think of an example of one I've actually seen. There's no rule that says they have to be the same. I just have never seen one where they're not all the same. That's all. But there's no rule about it. Good. So those are some examples of amines and how to classify them. Maybe some other examples of naming amines. I suppose you could call that tetrabutyl ammonium. Or maybe tetrabutyl ammonium ion. That sounds good. Something like that. Tetrabutyl ammonium cation, if you really want to. There's a couple ways of approaching it. Good, but other aspects of naming amine. Okay, this is really getting annoying. It's not the screen. It's like it's responding to my head or something like that. I promise there's no metal implanted in my head. I don't know what the problem is. Well, be that as it may. So much for some ideas on the structure of amines, but that's basically all there is to say about that part. They're just organic derivatives of ammonia. What about some of the properties of amines? Yeah, I think I do want another screen. First of all, amines are polar. No big surprise there. That's because of the nature of the carbon-nitrogen bond, regardless of what if I survive, regardless of what else is attached to the carbon or the nitrogen, that bond is going to be polarized towards the nitrogen atom. There's going to be a partial plus charge in carbon and a partial minus charge on nitrogen, because nitrogen is more electronegative than carbon. True, nitrogen is a lot closer in electronegativity to carbon than is, say, oxygen or fluorine or chlorine. So there are certainly more polar bonds than the carbon-nitrogen bond, but it's still considered a polar bond. There's still a significant electronegativity difference between nitrogen and carbon. We don't need to get into numbers. Like I said, I don't care if you memorize all of those Pauling electronegativity values. I can think of very few things I would rather you guys do than memorize a bunch of numbers. Good, so certainly they're fairly polar. As for primary and secondary amines, exhibit hydrogen bonding. No big surprise there. Just like ammonia does, just like water does. And let's not forget what hydrogen bonding is. A hydrogen bond is an intermolecular force. So it's going to be between two or more different molecules of the same, two or more different molecules. We'll just leave it at that. They can be the same compound or different ones. And so, you know, how do you show a hydrogen bond? Maybe by kind of a dotted line. Normally you don't show them unless you're specifically talking about hydrogen bonds. But it's an intermolecular force. It's something that exists between two different molecules, between the hydrogen of one and the lone pair on generally oxygen or nitrogen of the other one. So it's an attractive force that requires energy to disrupt. It's not a covalent bond. It's an intermolecular force. And so for that reason, we can expect certain properties to show up in amines because they're both polar, though they're certainly not the most polar of compounds, but they're both polar and exhibit hydrogen bonding. And this shows up in, first of all, and I'll give you some examples in just a moment, in properties like boiling point. Amines will have a higher boiling point than alkanes of a similar molecular weight. That makes sense because you have to put in extra energy to separate the molecules from one another and get them into the gas phase, right? In the gas phase, recall, all of the molecules are going to be very far apart from one another. And so you have to disrupt all of those hydrogen bonds in order to make that happen. That's what happens when you boil water. You're breaking hydrogen bonds. You're not breaking covalent bonds by any means, but you are breaking hydrogen bonds. You need to do that in order for the water to go from a liquid to a gas. And that's not just true of water. That's true of any compound. But any compound where you have a significant amount of hydrogen bonding, it's going to be harder to do that. And so you'll need to put in more energy in the form of heat, which shows itself in a higher boiling point, other things being equal. So that being said, the effect is less dramatic for amines than for alcohols. And I do have an example here. I sure don't expect you to memorize these numbers. So I'll put structures up here and we'll put their boiling point in degrees C. So the boiling point of propane, which actually, let me even do this. Let me put molecular weight also. Can I go MW for molecular weight? That's in grams per mole. And then their boiling point in degrees C. So the molecular weight of propane is 44 grams per mole. You can verify that for yourself if you like. Boiling point is minus 42 degrees C. And of course, I don't care if you memorize that. I'm not trying to get you to memorize numbers. I'm trying to illustrate a point. Let's compare to that. Let's compare to propane ethylamine. It's a pretty good comparison. Ethylamine is a molecular weight of 45 grams per mole. So it's almost the same. This is to show that the effects that you're seeing don't come from just how heavy the molecule is. Something else must be happening. And the boiling point of ethylamine is significantly higher. It's 17 degrees C, plus 17. Whoops, already have degrees C there. So we've gone up, what? 60 degrees, something like that. And that effect is mostly because of hydrogen bonding, maybe a little bit because of polarity too. If we were to compare both of these to ethanol, CH3CH2OH, that will now have a molecular weight of 46 grams per mole. So it's again in the same area. 1 gram per mole difference is not going to cause anything dramatic in terms of the properties, I don't expect. And the boiling point of ethanol is 78 degrees C. So again, we've gone up about 60 degrees. And this is showing that both of these molecules exhibit a fair bit of hydrogen bonding. However, ethanol is also significantly more polar than ethylamine is. And that explains why its boiling point is higher. Because now you not only have to disrupt hydrogen bonds, you also have to deal with dipole-dipole forces. And those require a certain amount of energy to overcome. And energy will be coming in the form of heat, meaning you need to raise it to a higher temperature in order to get it to boil. So like I said, the point here is not the numbers. I really don't care if you memorize the numbers. The point is that something is going on in these molecules. There's a trend here that does not have to do with molecular weight, because they all have essentially the same molecular weight. Something else is going on here. And I would hope that your Gen Chem professor showed you scads and scads of examples of things like this, where the properties, the relative properties of molecules depend on intermolecular forces. So this is just a review of intermolecular forces from Gen Chem. But that's really all I wanted to say about that. I didn't intend to go any further than that. Let me just make sure I'm not missing anything else. Nope. I think with that, we can begin to get into the reactivity of amines. At least let's spend the last, 10 minutes or so talking about preparation of amines. And we can leave other things like basicity of amines, properties of amine salts. That can all wait until next time. Any questions so far then? I feel like I haven't really paused for questions. Oh, yes. This one is ethylamine. I can tell you all of them. Why not? Ethylamine, this is propane. And this one is ethanol. You use that all ending for an alcohol. We'll formally discuss more how to name alcohols when we get to the chapter on alcohols. But probably if you had all taken a wild guess, OL sounds like a good ending for an alcohol. Good, other questions then? All right, well, let's talk about preparation of amines or alkylation of amines. First, I need to be able to spell preparation, which is apparently asking a lot of me today. And the idea here is we're going to turn ammonia into an amine, or we're going to turn one amine into a different amine by alkylating it, by adding alkyl groups. That's going to be the idea behind this. And this is one of the ways that that amines are made. It's not the only way, but it's certainly one way. And the idea is we're going to take well, I'd actually rather not do this by showing you a general case. I'd rather show you some particular examples. I think that will work best. Let's say that we took ammonia in large excess, and I'll explain why the ammonia has to be in large excess in a little bit. It's an idea we've run into before. The idea is going to be to avoid something happening that we don't want to happen, which I'll get to. Let's say that we treated this with, let me get my colors out again. Let's say we treated this with 1-bromobutane or 1-chlorobutane. So we've got, really rather that be black, doesn't really matter. Let's say that we treated 1-bromobutane with a very large excess of ammonia. And there are ways of doing this, to be sure. What we can expect to happen is that we will get that same butyl group attached to, wait a minute, I'm gonna go back to black. Attached to the nitrogen in the ammonia. So we're going to replace a hydrogen with that alkyl group. And in general, this is going to be true. The strategy is we'll take ammonia in large excess and treat it with some alkyl halide, preferably primary. If we were doing chapter 6, I'd be pointing out that this is an SN2 reaction. But that's almost a little beyond what I would have wanted you to get out of it. So suffice it to say now, certainly this is a substitution reaction. We already know about those. In a substitution reaction, you have two groups switching places. And that's exactly what happens here. One of the hydrogens on ammonia switches places with the halogen. It doesn't have to be bromine. Chlorine or iodine would also be fine. But one of those hydrogens, wait a minute, not with the halogen. It's, no, the hydrogen winds up attached to the bromine. The hydrogen changes places with the alkyl group. That's a much better way of putting it. And so you do wind up with HBr or HCl or HI, depending on what you started with, as an inorganic side product. Whoops. And as usual, it's only because we care so much more about the major organic product that we care that much less about the inorganic side products. If you wanted to write a balanced equation, then you would want to show that. But as you'll have noticed, we organic chemists are pretty sloppy at times about balancing equations for mass, only because we're so focused on the organic product that we care much less about the inorganic side products. That's what I would say. So this is an example of that type of reaction. And it is one way of making primary amines. In other words, in general, if you treat ammonia with any alkyl halide, preferably primary, so preferably CH2 attached to the halogen, that's for the best results, I would say, then you wind up with a primary amine of this type. And again, this doesn't have to be a bromine. It can also be a chlorine or an iodine. I would say probably not a fluorine, though. Fluorine is so different from the other halogens. I've heard some people say it's almost not a halogen. Well, it is. But fluorine is very different from the other halogens. And in this case, it's that the carbon-fluorine bond is very strong, and it's very difficult to do that substitution reaction in alkyl fluorides. But chlorides, bromides, or iodides will all work. Just to give one more example of the same type of idea, let's say that we took diisopropylamine in excess, and we treated it with methyl iodide. I would then anticipate that you're going to switch the hydrogen and the alkyl group. So you would get methyl diisopropylamine as your major product. Again, assuming a large excess of the diisopropylamine. And you would, of course, still get HI. That would be the inorganic side product. We're mostly concerned about the organic product, however. And I would love to do one more example since we have the time. In fact, I think I will. I'm just trying to figure out a way to do this without, well, here's what I'll do. Does that make sense so far, though, before I finish with one last example? Oh, actually, I have it on me, I think. I found the funniest thing yesterday. Since I'm actually falling into this right now, and yes, it's a meme, I thought of all my students when I saw this, and I said, oh, those poor kids. Yes, here it is. Hopefully I can open a JPEG file. Invalid value for registry. Dang it. How can that possibly be? Open with. How about GIMP? That would work. See if it gives the same error message. Or does this computer? Yeah, it has GIMP on it. GIMP is kind of overshooting what you need. Something much less fancy than that would do it. See if it gives the same error. I mean, here's a file on my USB drive that I'm giving you. Oh, geez. I knew I aimed a little too high. Well, I might not get to do that example, but if you can see this picture, it'll make everything worthwhile. Or is it already really old and everyone's seen it already? The one that says example in class and problem on assignment. Forget it, this is going to take forever. Basically, it said example in class, and it is a drawing of a triangle. And then it says, example and assignment is this geometric spider that's kind of hard to draw, you know? And I thought, my poor students. Well, clearly it's not going to even open GIMP, much less my file. So I would have liked to do another example. Maybe we'll start with one next time. But other than that, that's basically all I wish to cover today. So have a great day. See you all on Wednesday.